Thin silver coatings in the range of a dozen nanometers or so can be used for a number of applications. These can be flexible transparent electrodes. They can be used for energy-saving windows, even in some metamaterial innovations. But there are certain intrinsic challenges that come with using this platform. You need to control the thickness and the morphology of these layers quite precisely, and silver, despite being a noble metal, does have a certain chemical vulnerability. And more importantly, you need to balance both of these issues at the same time. In the present context, we're going to be talking about anti-reflective coatings, or AR coatings. So the typical dielectric AR is going to be highly transparent and chemically durable, but it's going to be susceptible to cracking. Whereas on the other hand, metallic AR, we have to contend with the absorbing aspect of metals and with the chemical susceptibility of silver. However, it's going to be much more resistant to cracking, and depending on the thickness of the silver layer, it can be a much better AR. As you can see down here, if we model the optimum RV, that is the visible reflection of these stacks, if we go from a 15 nanometer silver layer down to a 6 nanometer silver layer, we have a drop in the projected RV from 1% all the way down to 0.05%. So to create a good anti-reflective coating, we need a thin silver layer, but we also need to have a continuous silver layer if we want it to be transparent. And unfortunately, silver grows in a Volmer-Weber growth mode or island growth mode, where as the thickness increases, you're going to go from these separate islands, which are going to slowly agglomerate until they create a semi-continuous percolated network, which is going to be conductive, and then finally coalesce as all these little gaps close. So how do we create a continuous silver layer at low thickness? There's a number of things to do. We can control the surface mobility of these silver atoms. We can increase the nucleation density for silver islands. But perhaps more importantly, or more relevant to this work, we want to engineer the surface energy and change the mismatch between the substrate and the film. So typically, we can do this by increasing the substrate surface energy by using a good one like zinc oxide, or interestingly, we could try to lower silver surface energy. And I'll say more on that in a moment. But first, let's talk about how we're going to be depositing these films. We're going to be using a CMS-18 sputtering system with 4 magnetrons, with DC and RF power source, a good base pressure, and importantly, we have an in situ ellipsometer set up here. And what this is going to allow us to do is to monitor whether silver films are continuous or not. Essentially, the way we're going to go about this is we're going to fit the optical properties of the substrate, then deposit a continuous silver coating at a high enough thickness that we're out of doubt certain that it's going to be continuous. And then we can fit the optical properties or refine them until we have a model that very well describes the nature of our silver film. So then fitting the thickness backwards in time on all of the previous data, what we're going to get is an error that's based on how well these optical properties fit. So at very low thicknesses where the film is completely discontinuous, you're not going to have a good fit and you're going to have this very high error here. And this transitional point where the error decreases and it evens out to this kind of minima in the MSE is where you're going to have a transition from continuous to discontinuous films. So as mentioned earlier, what we want to do here is not only increase the substrate surface energy, but also decrease the silver surface energy. And the way we're going to do this is by sputtering in an argon-nitrogen mixture. Essentially what this allows is temporary bonding with the silver and nitrogen atoms. What this is going to do is it's going to lower the silver surface energy, but it's not going to create a permanent bond. It's actually quite unstable. As soon as more silver is deposited, these nitrogen atoms desorb and then flow out. So you're left with silver that has its normal optical properties that's quite pure, but you still get to have the advantage of the shifted morphology and the shifted growth process. And as we can see looking at these in situ ellipsometry results, there's quite a large advantage to doing this, especially without zinc oxide, there's this very dramatic shift where the continuous film forms around 6 or 7 nanometers as opposed to 10 or 11 nanometers with the addition of 50% nitrogen in the sputtering mixture. You can see that there is still some advantage to using a zinc oxide seed layer. You can arguably say that it converges lower, but more importantly, there's this peak in the MSC that's going to be a little bit lower that's indicating a smoother, more continuous-like morphology. But the effect is definitely diminished when you compare it to its use with argon sputtering, where you have a markedly lower threshold for continuous film formation. And now if we look at these different types of silver deposit on these different substrates, we're going to find that there's an important difference in the performance. As you can see here, silver deposited without nitrogen has much higher sheet resistance, especially if it's deposited on silicon nitride as here. There's really a huge gain in using the zinc oxide seed layer. But if you go to silver deposited with nitrogen, that's not really true anymore. We actually have a lower sheet resistance when using silicon nitride, not so much because it's a bare seed layer, but because we don't need a good seed layer, and a 33 nanometer thick layer of zinc oxide is actually going to be quite rough, which is something that's difficult to mix properly with the 6 nanometer silver film. But yes, you can see that using this, we have very low absorption. We managed to get some great anti-reflective properties. So what are we missing? Why don't we just take this silicon nitride with silver deposited in nitrogen and call it a day? We haven't seen anything about durability yet. And we're going to be testing that by submerging these samples in an aqueous sodium chloride solution, which is either going to be at 5.6 grams per liter at room temperature or 200 grams per liter at 50 degrees Celsius. And while these samples are immersed in this solution, we're going to be tracking their optical properties with in situ transmission. So if we test this in those gentle testing conditions, as I was mentioning, in a very simple configuration, silver deposited directly onto glass with silicon nitride to protect it, we find that silver deposited nitrogen is much more susceptible to corrosion than regular silver is. Whereas regular silver degrades completely in about 1200 seconds, silver deposited nitrogen degrades in about 400 seconds. And the reason for this is that the crystallite size of silver decreases with the amount of nitrogen. This is normal, this is expected. We're lowering the threshold for island formation. So this is going to bring about these smaller crystallites and smaller grains. And with smaller grains, we're going to have more grain boundaries, which is going to increase diffusion of silver to corrosion sites and of corrosive products to the silver layer. However, it's interesting to note that if we add the zinc oxide seed layer, not only is the crystallite size increased quite a bit, but we also see that it's much less dependent on the amount of nitrogen. So to maximize durability, we need large grain sizes. But to have a film that coalesces at a low thickness, the techniques involve having a reduced grain size. So how do we balance these two things? Of course, using a zinc oxide seed layer becomes an obvious choice, where it's going to promote coalescence and crystallinity at the same time. It's also going to increase its interfacial energy with the silver layer, which is going to limit Kirkendall diffusion. And we can also optimize our use of silver and nitrogen, seeing as the grain size is increased by lowering the nitrogen content. But if we lower the nitrogen content down to 5%, we still have about the same benefit on coalescence. As you can see here, the MSC is quite a bit higher at low thicknesses, indicating that there's different morphology during the growth, but it does rejoin these other curves at about the same thickness of 6 or 7 nanometers. So we're expecting to have about the same effect on coalescence while having larger grain structure. So despite the previous improvements, there are still some adjustments to make. We're going to add nickel chrome nitride as a protective layer. It's a well-known remedy for silver durability issues. we're going to be using 80% nickel to 20% chromium. However, it should be noted that we're still going to be optimizing the silver layer here because we want to be able to use as little nickel chrome as possible. The addition of only a few angstrom is going to increase our absorption by a few percent, so it needs to be limited on that aspect. But also, if we use a very thin layer, it can help coalesce the silver layer, whereas a thicker layer is going to have the opposite effect. So going to these accelerated testing conditions with the 50 degrees Celsius temperature, 200 grams per liter of sodium chloride, and 0.2 nanometers or 2 angstrom of nickel chrome nitride on each side of the silver layer. You can see here that with the silicon nitride seed layer, we have a much lower performance with degradation at 800, 600, and 200 seconds of exposure for 0% nitrogen, 5% nitrogen, and 50% nitrogen. So you can see that there's a close relation between the degradation and the nitrogen content. However, the same is not true when depositing on zinc oxide. As I was saying earlier, the crystallite size is going to remain fairly stable and much larger than it would be usually. So you can see that this affects the durability very, very positively. We don't have any obvious degradation, no obvious change with the nitrogen content. So despite that these coatings are fragilized, they're not going to delaminate entirely the way these silicon nitride-based coatings are going to. So now that we have durable layers, we can look at performance again. And first and foremost, I'd like to point out the huge gains we get to coalescence with the addition of this nickel chrome seed layer with silver without any nitrogen. You can see that its absorption is now very much on par with the other types of silver. And this is interesting because it kind of creates a kind of trade-off situation where if we have silver without any nitrogen, we don't need to use zinc oxide and we can still get good performance. On the other hand, if we use zinc oxide with 50% nitrogen, we get the best optical properties or the best performance of DAR at 0.2% reflection. And between those two, if we use 5% nitrogen, we have a somewhat less good reflectance, though this could be due to minute changes in the dielectric layers. We get a significantly lower absorption of about 1% lower. And this is quite interesting because it also comes with a slight decrease in the sheet resistance for this layer, which suggests that the increased coalescence and the increased grain size at once being in between these two is giving it better conductivity. In conclusion, we've created conductive, flexible, and anti-reflective coatings using ultra-thin silver films. We achieved these by sputtering the silver in a mixture of argon and nitrogen, and we were able to highlight the compromise that's required between early coalescence and large grain structure to achieve durable and transparent silver-based coatings. And this compromise was reached by using the appropriate seed layer, zinc oxide doped with aluminum, as well as nitrogen doping and nickel chrome nitride protection. Putting all of these together, we get the durable, anti-reflective, transparent coatings that I was showing you earlier, namely the one deposited on zinc oxide with 50% nitrogen, which is quite impressive with 0.2% visual reflection from the front side, 87.5% visual transmission, a sheet resistance of around 20 ohms square, and it resists desaline corrosion testing at 200 grams per liter and 50 degrees Celsius for over 20 minutes. So thank you for listening to this presentation. I'd also like to thank my colleagues at the FCSEL, my friends and my mentors for their help and their support throughout this project. Also our industrial partner Essilor for their part in their funding and valuable insight throughout the project as well. And of course, the SVC for allowing me the opportunity of coming at least virtually to the SVC and to have this presentation. It's a great opportunity. Thank you very much.